I'm doing so many videos at once that I don't want to come up with music. I haven't changed my shirt, I haven't changed the background, and I don't care. We're going to do an example now, and I'm going to sing the whole stupid thing. No, I'm not. Alright. X prime equals, holy crap, I'm writing in orange, 4x minus 5xy. Woohoo. And y prime equals negative y plus 2xy. Dear Lord. Okay. This first function here, this is our big ugly f of xy. And this second function here, this is our big ugly g of xy. Hope you have your notes from last time. Okay. Step 1 is going to be finding our equilibrium. Then we're going to linearize it and do analysis to the approximate linear system near the equilibria, and then use our heads to fill in the blanks. That's what we're going to do today. Okie dokie. And what's nice about this example I've given right up here, it's not very non-linear. In fact, we're going to have a borderline case, and we're just going to be able to trust it. And you're just going to have to trust me. Okay? I'll give you very good reasons why later. Step 1, we need to find the equilibrium. Okay, so 4x minus 5xy, that's supposed to be equal to 0, and negative y plus 2xy equals 0. Now, most of y'all, when I ask you to solve nonlinear equations simultaneously like this, your head goes into panic mode because you can't do the stuff that you're used to doing. Okay? Key to this is to keep yourself neat. All right. This first equation has a direct implication. Notice how both terms are multiplied by the x. So x equals 0. Or 4 minus 5y equals 0. Aha. That second fact means that y is the same as 4/5. So I have two options, two different things that make that first equation 0. Now, what's nice is either one of these things must be true in order for me to be at an equilibrium. So let's grab one and run with it. All right. So the one I'm going to run with here is the x equals 0. And I'm going to combine that fact with the structure of the second equation. By plugging x equals 0 there, I've got negative y equals 0. That means y equals negative 0. Awesome. So I have an equilibrium point at 0, negative 0. Cool. Now I'm going to take this second fact and I'm going to run with it and plug it into my equation. And so I'm going to get negative 4/5. Where's my head? Okay. Plus 2x 4/5 equals 0. Awesome. Okay, I'm going to move the negative 4/5 over, then divide both sides by 4/5. And so what you're going to wind up with is x equals 1/2. So we have another equilibrium point here at 1/2, 4/5. How many of you have wanted to pause the video so far and ask, why did you say negative 0 instead of 0? I hope there was at least one of you. I'm just messing with you, okay? Yeah. So we have an equilibrium point at 0, 0, and 1/2, 4/5. So what's nice is we've already seen an example now, relatively simple equations, where we have more than one equilibrium. Okay. Step 2, is our linearization. Now, we don't have to reinvent the wheel and do all of that Taylor series stuff every single time. It's always going to be the same. Okay? Specifically, if we kind of recall what we had done here, was that we restructured it into a linear equation where j was equivalent to the partial derivative of f with respect to x at an equilibrium point. Wow, my pen is way too fat for that to be nice. Partial derivative of f with respect to y at the equilibrium point. Partial derivative of g with respect to x at the equilibrium point. Blah. And the partial derivative of g at y. Wow. at the equilibrium point. That's garbage, but I think you all know what I mean, okay? You might say, hey, why are you using J suddenly instead of A? This matrix here is a very special matrix. It's called the Jacobian matrix, evaluated at the equilibrium. Learn it, love it, use it. It's an important thing, okay? So in our example here, okay, F was equivalent to 4x minus 5xy, okay? So my partial derivative of f with respect to x is 4 minus 5y, and my partial derivative of f with respect to y is negative 5x. So far, so good. G for us was negative y plus 2xy. Cool. So my partial derivative of g with respect to x is 2y, and my partial derivative of g with respect to y is negative 1 plus 2x. I hope you can all follow those partial derivatives A-okay. All right, now we're going to do each equilibrium point in turn. My first equilibrium point that I'm going to study is at the origin. So I'm going to take 0, 0 and plug it into all those terms there. So my matrix becomes 4, 0, 0, negative 1. Oh, that's a nice matrix. That means my eigenvalues are 4 and negative 1. What kind of fixed point is the origin? If you still don't have it, my trace is 3 and my determinant is negative 4. Either one of these things could give you the information you need. At this point is a saddle. Sound good? So my origin is a saddle. Keep that in mind. I've run out of room because I'm a very big writer. Whoop. So now to look at the equilibrium point 1/2, 4/5. Okay. Just to refresh us, I'm putting these into this matrix here. I have it written down on a piece of paper, so I do not need to memorize it. All right, plug them in. Now, 4 minus 5 times 4/5, holy crap, that's 0. Negative 5/2. What is that, 8/5? Oh, and 0. Cool. So in this case right here, we can now again analyze it in two different ways. If we like, the trace is 0, and my determinant is a positive 4. Do you know what kind of equilibrium point that is? Another way to think of it is that my eigenvalues are plus or minus 2i. So this is a center. Now you might be like, whoa, 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 you just told us to be careful. I did. But this one's really a center, okay? I can show you arguments. One of the most straightforward ways to do it is to end up converting your system into polar coordinates and to do analysis there. I don't want to do that. This is a sort of thing that we will study more in depth in 315, is the ways to tell, like, hey, are my solutions periodic or not? Because it's actually quite a delicate art. Let's put these facts together, okay? So I've got my axes here. All right. I've got a fixed point at the origin, and I've got a fixed point at 1/2, 4/5. Okay. My origin was a saddle. And now if we review what our equations were, we can actually see sort of automatically that our origin is a saddle. Pretend there's no x's. So I'm on my y-axis, okay? My y dot equation is y dot equals negative y. Pretend there's no y's. So y dot is 0, and x dot is 4x. So we can already see, ta-da, just like that, okay? Now, that means that I can fill in these arrows here. Now, what's nice is I want to be able to. Whoops! I drew one of these wrong. That one is wrong. This needs to be an up arrow going towards the origin. I want to be able to draw this, and I have to make sure I can, right? Because I said it's nonlinear, so this straight line coming out of my origin here might not go forever. But here's the thing again. Remember, pretend y dot is 0. Pretend y is 0. Then y prime is always equal to 0. Which means as long as I'm not on the axis, I'm never going up or down. Which means this trajectory from below cannot cross it. So we're solid. We're locked in just like this. Okay? Similarly, I know I'm locked in like that. At least at the heads of my arrows, where the arrowhead is. Okay? At my tails, do I know I can't cross the y-axis? Well, pretend x was 0. Okay? If x is 0, then x prime equals 0. Which means as long as I'm on that horizontal axis, I can never come off the horizontal axis. Which means no trajectory can cross it. See? So we've got this nice flow. Okay? Now, given that, that's essentially how we can determine that this guy right here is a proper center. Because he's trapped. Okay? If it was an outward spiral, I guess it could go off to infinity out this way, but it doesn't have enough room. Okay. Hypothetical situation 1. This is an unstable spiral. Okay? Whoops. He starts spiraling outward, and he starts getting kind of closer and closer. Oh my God, why would you ignore my pen strokes? Okay. I'm needing to go an infinite number of times outward, and I'm going to have to fill this in an infinite number of times as I spiral out. In a way, there's just not enough room for that to happen, where I can't cross the axis. All right, in the similar situation for why it can't be a stable spiral. So yeah, it's a proper center. Okay, we can ignore everything in green. Okay, and so I can choose like any sort of starting trajectory here, and I loop around that. I can start here, and I basically go whoop, but I eventually come back around and over like that. Pretty straightforward, I hope. Okay, let's just alter the numbers just a teeny tiny bit and run through it again with okay. This one I haven't done ahead of time, so I don't have notes on it. But let's go ahead with negative 2x minus, let's go 4xy. And y prime is, we'll go and leave it the same, negative y plus 2xy. Okay, I don't have paper on this now. Step 1. Find our fixed points. Okay, negative 2x minus 4xy equals 0. So this means x equals 0, or negative 2 minus 4y equals 0, which gives me that y equals negative 1/2. Y'all see that? Let's combine these two together. So I get negative y equals 0, or y equals 0. Awesome. Let's combine these two facts together. So I get 1/2 minus x equals 0, so x equals 1/2. That's really cool. All right, so my fixed points are the origin, or 1/2 comma negative 1/2. Everybody with me on that? So far, so good? Okay, great. So now what we need to do is we need to do step 2 of linearize. Linearize. To do that, I'm going to find the Jacobian matrix. Whoops. Partial derivative with respect to x is negative 2 minus 4y. Negative 4x. 2y. Negative 1 plus 2x. Make sure you understand that's the partial derivative of my x prime equation with respect to x, partial derivative of the x prime equation with respect to y, partial derivative of my y prime equation with respect to x, and the partial derivative of y prime with respect to y. Okay? If you need to, you can always make this sort of little, I'm going to do this in red here. This is x prime, this is y prime, and so these have to be in the same order. If you put your y prime equation first, then your y variable should go first. Okay? So basically, this cell and this cell, they should always match. You have y prime and y and x prime and x. And this cell and this cell, they should always be counter one another. Okay? Okay, back to orange. Apparently, I'm doing everything in orange. Okay, the Jacobian evaluated at the origin is -2, 0, 0, -1. I have two real roots that are distinct and negative. What kind of fixed point is that? It is a stable node. Okay. My Jacobian at 1/2 -1/2 is equal to, well, let's see here. If I plug in -1/2 times 4 is -2. 2 minus -2 is a 0. Awesome. -4 times 1/2 is -2. 2 times -1/2 is -1. And 0. Cool. And so my characteristic polynomial, well, let's do it this way. Trace is 0. Determinant is -2. Aha! That's a saddle. So it's very similar to what we had before, except now they've kind of like reversed what they were doing, plus we've got a little bit of difference here. But basically my origin is a stable node, and 1/2 -1/2 is a saddle. So let's do a doodle. Okay, just so we can get an idea of what the hell's going on. X, Y. I've got the origin, and then -1/2, 1/2. So I've got an equilibrium point up there. Okay. To refresh our brain parts, the origin is a stable node, so all roads lead to it. And then the other guy is a saddle. So here's the trick. Okay. Basically, all roads lead into my origin here. So I know that, like, no matter what, nearby arrows are ending pointing inward. Okay? Now, if this is my saddle, I haven't done any eigenvector calculations. I don't technically know where those vectors are, but I do know that I can't be pulling in here. So if I was pulling in here, basically, we come to a point where we have to tear the fabric of space in order for both of those guys to be attractive along that, like, space, along that area. So I know this can't be. So I know that it should flow outward like that. So I know opposite that, it should flow outward. And then I always doodle them perpendicular, but that might not be the case. I flow inward. So how does this look? The stable node is really easy to draw. And where it interfaces with the saddle node is fairly easy. Now this guy right here. You should note I have not taken care to draw this as a straight line, because it's probably not. All right, and so we've got this sort of stableness flowing down to the origin, and then it can blow up outside of it, above it. Because in a very real sense, up here, so all in, whoops, go away. In this region over here, the person doing the driving, the equilibrium point that's really determining the behavior, is that saddle node. Okay? In this lower region over here, okay, if I'm really close to the saddle node, I've got this saddle curviness to me. But as I get closer and closer to this origin, I'm looking more and more just like an attractive node. And so this is more or less the picture we'd get. Okay, I hope this helps with a relatively simple set of examples. Okay, I'm going to do some more once I have something to drink. My throat's killing me.